Welcome to the class meeting 8 of EECE574, the graduate level probability and random processes. This is a recorded version of the class meeting, and it's a kind of makeup class. Let me do the announcements first. Homework 4 will be assigned. I haven't yet uploaded, but by the time this video lecture is uploaded, you will see the homework 4 available from the PLMS. Handouts for chapter 3 is updated, so please reload it. Passwords are as usual. And recorded class meetings are continuously uploaded to the YouTube channel, and the annotated PDFs are also available from the lab course homepage. Next, the messages from the instructor. Last time I talked about divide, conquer, and integrate. This is very important when you really do some problem solving, because you are given the original big problem, you divide it into a small part, you apply the simplification and visualization techniques, and then you make it grow to the original size. You do this process for all fractions, and then you integrate them to solve the whole entire problem. So this is a very important message: divide, conquer, and integrate. And another message I have given you is that you need to change the value system. When you are an undergraduate student, you regarded most of the things as stage clear. You get the grade, you pass the mandatory course. But as far as you have become a graduate student, this value system does not work. You have to have a kind of growth mindset. You have to continuously improve yourself. It's a kind of kaizen in Korea, 개선. You have to improve yourself in every aspect of your research, your personality, and everything. So this is very important. Another thing is this one I want to give you today is you have to keep in mind that whenever you learn something new, you have to search for something that has commonality with what is currently inputted, and then also find the similarities and difference. By doing that, by finding the commonalities, so for example, you have set A and B, this intersection part becomes the commonality. Then instead of having this entire area occupying in your brain, you can have a smaller area with less area occupying in your brain, so that you can squeeze in more knowledge in your limited brain. Another thing is that by trying to find commonalities, you also end up with similarities. Two things may not have exactly same components. However, finding the similarities allows you to compress the data and organize your knowledge. So that's very important. Also, in order to try to differentiate two things, you can have a better understanding of the original items. So as a graduate student, whenever you learn something, keep this in mind. Find commonalities and similarities, and also try to find differences from what you already know. Another message today I want to give is that whenever there are some two competing things and you don't know which one to choose, try to find the pros and cons of each competing side. Sometimes the pros of one side becomes cons of the other side. Sometimes pros can be shared, but cons are not shared. By trying to find these pros and cons, then you can clearly find the superiority of one choice to the other choice. So this is one of my message. Okay, now let's move on to our overview. we are still working on here in chapter 3. As I originally planned, we've already have done this chapter 5, but it seems that I'm speaking or talking too much on the details of chapter 3. It appears that the undergraduate level knowledge on these operations on one random variable may a lot differ from the graduate level. So I kind of underestimated what you should know as a graduate student compared to undergraduate student. Anyway, it is good for you to take enough time to understand what is new and what is improved about the knowledge on these topics. Anyway, today's objective is to finish chapter 3 because we are too much behind the schedule. So let me be a little bit quick. However, still, as always, we have something to clarify from last class meeting. So in the last class meeting, as you see in this review, we talked about non-central moments, especially the expectation of non-central moment under the constraint that the random variable is non-negative with probability 1, or in other words, almost surely. And then here we use the exploited kind of Stieltjes integral, and our result was something like this. So this does not involve Stieltjes integral, but in order to derive these results, you need to rewrite the nth order non-central moment by using the Stieltjes integral, like value times d CDF of x. And then you need to visualize what this integral means, and you apply this additional constraint to get this result. Anyway, so this was one of the very, very important topic. And as far as I remember, this result was not taught when I was an undergraduate student, but one of the most important result I was taught in the graduate level probability and random processes. And even I told you that the showing or proving this result appeared as one of the qualifying exam problem when I took the exam. And at that time, I got just partial credits. So as far as you can, you fully understand the theory behind, the approach behind the derivation of the results, that is the Stieltjes integral and visualization, you are now at a better stage than me in 20, or let me see, 25 years ago. Okay. Now, then we define the standardization of a random variable by using two important moments. So suppose we have a random variable x, and we have its mean value mu sub x and its standard deviation sigma sub x. As you are my students who was taught by me, you now know and see that this ratio has a unit list. This ratio does not have any unit. So this is a unit list quantity. And we usually call this as z, and sometimes we call this value as z score. Anyway, this is kind of performing centralization of random variable and kind of normalize the second mean. So what you have is that the expectation of z is always 0, and expectation of z square, in this case, same as the variance of z, equals 1. So the first order and second order has very interesting results. And this skewness is related to the third order moment of the standardized value, sorry, to the z to the cube. So z to the cube is called the skewness, and it's a kind of measure of centeredness. So if it does not have symmetry, this skewness deviates from value of z 0, and If it is quite close to 0, then you can say that the distribution PDF of the random variable is very symmetrical. What is related to the fourth order uh, kind of central moment after normalization is called the kurtosis. Sometimes people subtract 3 from this value because given a, for example, given a Gaussian random variable x, all the odd order central moments are zeros, and even order normalized centralized moments have something very interesting, especially the fourth order central and also normalized, so-called standardized moment of a Gaussian random variable becomes 3. So that's why some people subtract 3. Some people define kurtosis as the fourth order moment of z. Some people define it as a fourth order moment of z minus 3. And that 3 appears because the Gaussian random variable has fourth order moment of z value 3. Anyway, this is a measure of tailedness. So if the tail probability of a certain random variable is very, very small. So as Gaussian density is a light-tailed probability e to the negative x minus mu x squared divided by 2 sigma x squared. Of course, you have some scaling thing. Then this is Gaussian density. And as you see from the PDF, the tail decays very fast. It's quadratic exponential. And in that case, this kurtosis becomes 0. So if the tail is not light, that means tail is heavy, then this kurtosis becomes larger, becomes more than 0, but very large, something like that. So the kurtosis is a kind of the measure of tailedness of a distribution. Anyway, after that, as I just told you, there comes what you want to more clarify. It is related to the moment and moment-related inequalities. So I'm going to skip the reminding the definition of the moment generating function and its relation to Laplace transform because I explained it in detail and there was nothing add. But about these inequalities related to the tail and the probabilities, let me give you some other viewpoints. So first, Markov inequality. Second, the Chebyshev inequality. The third, the Chernoff inequality. I told you that you'd better understand the Markov inequality as a kind of related to the first order moment. And Chebyshev inequality is related to the second order moments. Here, if I say second order moments, then it not only talks about the second order moment, but also is lower than second order, which means that first order is also involved. Chernoff inequality is not related to the third order inequality, it's related with the general nth order, nth order moment. So let's see. So here goes the figure related to the Markov inequality. So take a look at this part. So, yeah, change the colors. So here, I draw a graph as a function of x, graphs of two functions. First one is x over a. Here we assume a is positive. So actually, it extends to this. And I also draw a unit step function u of x minus a. So the value is 0 until a, and it jumps up and becomes 1. If we assume this u of x is right continuous, then probably I have to fill this point up and leave this point as blank. Now, let me ask you a question. Can you give me an inequality from these two graphs of these two functions? And you can easily see that this line is always above or equal to this line or this function as far as we are concerned with x non-negative. So for every x non-negative, x over a, sorry about that, this must be lowercase x, x over a is greater than or equal to u of x minus a. See that? This graph is greater than or equal to that graph. So it's kind of obvious. Of course, we have to pay much attention to the equality condition. Equality occurs when x equals 0 or x equals a. But anyway, so we have u of x minus a less than or equal to x over a for all x greater than or equal to 0. Now, what if we replace this lowercase x with a random variable, which is non-negative almost surely? Then we can say, of course, for every realization of that random variable x, we have this. Okay, so we can say this. Since for every realization we have that, we can also consider the expectation of the left-hand side and right-hand side, which is the same as we multiply density of x on the right side and left-hand side. Because the PDF of a random variable is always non-negative, the PDF times this u function and PDF times x minus a function still keeps this inequality. And then if we integrate that, then we still have the inequality. So eventually we have this inequality where expectation of u of capital X minus a less than or equal to expectation of capital X divided by a. Now, what is the left-hand side? It's similar to the expectation of an indicator function, where the indication occurs when x is greater than or equal to a. So the left-hand side is nothing but this probability of x greater than or equal to a, and of course, which upper bounds the probability of event that x greater than a. Because x equals a, that event is removed, we have the probability less than or equal to this probability. Now, let's take a look at the right-hand side, which one is just copied here. Since expectation is a linear operator, we can write it this way, mu x divided by a. So what do we have? We have the Markov inequality. So right tail probability. So x greater than or equal to a is upper bounded by a what? Inverse linear function of a, right? And the coefficient is the mean value. So the tail probability, if x is non-negative random variable, then the tail probability is upper bounded by the mean divided by the tail start point. Now we can move on to the Chebyshev inequality. So let me grab this part. Now the figure is slightly different, but almost the same. Let's take a look at the graph of a quadratic function of z. And this curve is z squared divided by k squared. And as you can see here, you have this unit step and that unit step, lower than the quadratic function. So you can write it this way. The quadratic function of z square divided by k square, upper bounds u of z minus k, which is this part, and u of k plus g, that is this one, right? So you have this inequality for all z real. Unlike the Markov inequality, you don't need non-negativeness. This is just true. Parabola, upper bounds, this curve, right? Now, similar to the Markov inequality, you take the expectation of both sides, replacing z with a random variable. Then we have this result. The left-hand side means that the absolute value of the random variable z realized is greater than or equal to k, where k is assumed non-negative. And what is right-hand side? If z is the standardized value of random variable. So if z equals, let's say, x minus mu x divided by sigma x, then the second order moment of z is 1. So what do you have on the right side? This is your right side. So you eventually have the tail probability of z upper bounded by k squared. And if we replace z equals x minus mu x divided by sigma square, we have that one. And now it looks familiar to our well-known Chebyshev inequality. Of course, you can square it without changing the event inside this probability operator measure. Okay. And what about the Chernoff inequality? Let's draw something similar for the Chernoff inequality. And here goes the figure. We focus on exponential function. This exponential function is very interesting. It's e to the nu times x minus a. So what is that? It's e to the nu x left shifted by a. Right shifted by a. In this case, a is negative, but it doesn't matter as far as nu is not negative. And this exponential function upper bounds what? This unit step function. What is that? This is u of x minus a. Be careful, the horizontal axis represents x. So as a function of x, e to the nu times x minus a always upper bounds u of x minus a for all x real, as far as nu is non-negative. What if nu equals 0? The exponential function becomes 1, and 1 is greater than this unit step function, greater than or equal to the unit step function. So the inequality still holds. Now we do the same thing. We take the expectation after replacing lowercase x with a random variable x. Then the left-hand side expected becomes tail probability of x greater than or equal to a. And what about the right side? Right side can be written this way. Moment generating function times e to the negative nu a. So we have something like this. Now let's view it as a function of a. Then this is the right tail probability as a function of a, and it must reduce. But we don't know the shape of it. But the Chernoff inequality says that it's an exponentially decaying function. The upper bound is an exponentially decaying function, and whose scaling factor is m sub x of nu, which is the moment generating function evaluated that specific nu. Okay? So what does this mean? As far as you have the moment generating function well defined, then what? You can upper bound the tail probability of the random variable exponentially. So as I emphasized last time, this Markov inequality, Chebyshev inequality, Chernoff inequality are not just inequalities related with uh, moments. It's really something interesting. And Markov inequality is related to the inverse linear upper bounding of the tail probability. Chebyshev inequality is related to the inverse quadratic or inverse square upper bounding of the tail probability. And Chernoff inequality is inverse exponential, or you can say exponential upper bounding of the tail probability. So please remember these three figures I have given you today. Then you can always understand easily what's going on with these three inequalities. And also sometimes this trick of visualizing two graphs and taking the expectation may give you a chance to solve some important research problem in your future endeavor in your graduate course. So please remember. Okay, the last thing from last class meeting is the characteristic function, which is often denoted by capital Phi with subscript capital X, which means that this is a characteristic function of a random variable X. And we use omega as we've done in Fourier transform. And this is what? Expectation of e to the j omega x. So here, what is random? X is random. So you can write it as e to the positive j omega x density of x dx. What is this? This is the Fourier transform reversed, frequency reversed. So it's actually Fourier transform of f of x evaluated at omega equals negative omega, something like that. Okay, so it's related to the Fourier transform, and the convergence, if and only if condition for this transform is the function is absolutely integrable. And fortunately, the density function is always non-negative, so taking absolute value doesn't matter, and integrates to 1, which is finite. So every density function is absolutely integrable function. So you can say that characteristic function of a random variable always exists. So this existence is done. And since this is an integral form which involves the limit operation, as far as the value exists, it's unique because if limit of some sequence of real numbers or complex numbers exists, it cannot be ununique. It must be unique. Second one is that this characteristic function, as the name implies, it fully characterizes a random variable. In what sense? From the characteristic function, you can get by inverse Fourier transform the PDF, or in other words, CDF. So as far as you know the CDF, you fully characterize the random variable. That's why this characteristic function fully characterizes your distribution. So this is what we learned last time, and I reviewed for a long time, spending a lot of time because these three figures for Markov inequality and Chebyshev inequality and Chernoff inequalities are very, very important. Let me remind you, Markov inequality kind of is the unit step function in here. Unit step function is upper bounded by a linear function. Unit step function's combination is upper bounded by a quadratic function, and unit step function is upper bounded by an exponential function. Okay, now let's move on to the today's topic, transformation of a random variable. Last time I mentioned this one very quickly, but let me do it again. So here goes some deterministic function g, and you have a random variable input. And what was my first question? Yeah, the first question is, what is the output? What is y? And what was our answer? y is a random variable. Because you can write it this way. So here is the underlying probability space that models random experiments. And here is our measurable function x. And then here is our g function. Now, what we do is that we group these two together to define as G composition X of S. Then what? Since we assume this X is a measurable function and G is a measurable function, its composition is a measurable function. So what? This composition becomes a new random variable. That's why we call the output y equals G composition X is a random variable. Got it? So since the output is a random variable, we want to characterize this output. For characterization, there is a two-way. One is full characterization, and second is partial characterization. And we will talk about both of them. The first thing is full characterization. What do you mean by full characterization? Yeah. As far as we can find the CDF of the output, we are done. So let's take a look at the CDF of y. So what is the CDF? That is defined as probability of event that the random variable y has realization less than or equal to some value y. Okay, then what? Here, this is the event. And whenever we talk about the size or probability of event, whenever we have difficulty, we replace this event with the equivalent event. Now, possibly in terms of x. So our notation is g of x here. I can write it as g of x, which is y, less than or equal to y. So now I can, I may be able to find the probability of this event in some cases very, very easily. In other cases, very difficult or even sometimes impossible. In order to analyze, we divide the cases. So first, we assume that G is linear. So this is G of x, which is ax plus b. Actually, this function is not linear, but affine. So affine transform is a more precise explanation or description. Unless b is 0, this type of mapping is called affine transform or affine mapping. Now, if this is the case, what happens? Probability of event that what is gx? Ax plus b less than or equal to y. Now, we can write it again as ax less than or equal to y minus b. So far, so good. Now, what you want to do is to find an equivalent event that only involves, for example, on the left side, x. So you want to multiply 1 over x, or you want to divide both sides with a, but here comes the difficulty. If a equals 0, we can't divide. If a equals negative, then the inequality flips. So what we first consider is the case where a is positive. Then what happens? This equals the probability of event x less than or equal to y minus b divided by a. What if a equals 0? Then this is probability of what? Yeah, if a equals 0, then what happens? This is 0. So 0 less than or equal to y minus b. And what is this probability? What is this probability? Let me see. If a equals 0, y equals b. Okay? Or x can be anything. I don't know. It depends, right? It depends value of y. Yeah. This is not event. So what can I do? Yeah. So actually, this is not difficult. Yeah. In this case, don't do this. Yeah. So let me skip that one. What about a less than 0? Then x greater than or equal to y minus b divided by a. If a equals 0, what happens here? Y equals b always. Then the CDF becomes unit step function, u of y minus a. Okay? Now, let's further do this. What is this one? CDF of x evaluated at y minus b divided by a. This is CDF of x. Sorry. This is, I need to be careful. Greater than or equal to. Yeah. This is 1 minus CDF of x, y minus b divided by a, plus probability of event that x equals y minus b divided by a. Yeah, you can show that. And then from the CDF of y, if we want to find the PDF, what you just need to is to find the derivative. So when a is positive, you differentiate this one. What happens? You know how to do that, right? As you learned in high school calculus. That is simply 1 over a density of x evaluated at y minus b divided by a. What about this one? Unit step function differentiated becomes delta function. So delta of y minus b. Sorry, y minus see that y minus b. I'm sorry, y minus b. So what about this case? In this case, we must be careful, but as you see here, this value is constant, or which can be some positive number or 0, but after differentiation, it goes to 0. So if you differentiate that one, what happens is minus 1 over a density of x, y minus b divided by a. That's why you obtained that one, okay? Last time I just presented the result, but this is how you derive the result. So what is most important and what is most fundamental approach to fully characterize the output y of this function over random variable is to search for the CDF of the output. And then you systematically convert the event to an equivalent event, and eventually you use the CDF of x, the input of the deterministic function g, and you describe the probability using the CDF of x, and then if you want to find the PDF of the output, you differentiate the CDF. Got it? Now, so this is the first step. You have an affine function case. What if you have something different? So usually what we do is that after we consider affine, we usually move to the second order case because affine is related to the zeroth order, which is constant, and first order, right? If a is 0, then you have kind of zeroth order, which is constant, and a is not 0, you have first order. So the next step, natural step, is the second order case. So for example, you have something that squares the input and you have the output. So you want to find y equals x squared, but interestingly, you'd better do this one first when g is a monotone function. So let me do the case. So g prime of x is greater than 0 for all x. Let's focus on this one. You can have kind of piecewise monotonicity, but let's do this. Now, as we have done in the first case, we start from the CDF. And by definition, this is y less than or equal to y. And equivalent event is that you have g of x less than or equal to y. But what? You assumed that g is monotone function. It's strictly increasing. What does that mean? If you can define G inverse and apply to both sides. You have the inequality kept the same. So what do you have? This becomes probability of event that x less than or equal to G inverse of y, okay? Which is CDF of x evaluated at G inverse of y. Got it? In order to find the density function, you apply the result of differentiation for composite function. Now, let's consider a little bit different case where G prime is monotone, but is monotonically decreasing. Then what will happen? You can easily show that this inequality now flips when you apply G inverse to both sides. So simply you have that one. Then you can write it this way. Yeah. So you can find that this is very similar to that case, and this is very similar to that case. Actually, the first two cases were special cases of these two, because affine function with non-zero first order coefficient is either monotonically increasing or decreasing. So there shouldn't be something special. That's why we focus on the monotone case first, then we consider squaring device case. So let me talk about the squaring device case, which means that the deterministic function is quadratic. I need more space, it seems. So let me push more this page. By the way, this bracket goes here. I will talk about this soon. Okay. So let me move to this third case. And we'll talk about the general case. What if we have a squaring device? Then the CDF of y is probability of event that y is less than or equal to y, which is x squared less than or equal to y, which is probability of x, assuming, okay, be careful. Here, let me draw. So this is x. You have x squared. And let me use y0 because this is labeled y. So what if y0 is negative? If y0 is negative, this is an empty set. So equals 0 if y0 is negative. What if this y0 equals 0? Then x squared equals less than or equal to 0, which is probability of x equals 0, right? What about y0 positive? Then now you set y0 and draw a line and find that, okay, here to here, we have x squared curve less than or equal to this y0 value, which projects to this closed interval. And what is the closed interval in terms, what is this closed interval? What is the probability of event that you have x in that closed interval? That is CDF of x evaluated at, this is square root of plus positive square root of y, and this is negative square root of y0. So you have square root of y0, and you have to subtract the square root of negative y0, but you have closeness, so you add probability that x equals square root of square root of negative y0. Now, once you obtain the CDF, you can obtain the PDF by differentiating that. And let's focus on a special case where the random variable x does not have this point mass, or you can still have that point mass because after you differentiate that, it will disappear. So let's consider the case where you have y0 greater than 0, or let me see, yeah. And then we differentiate this one, and what happens? We have the density of x, square root of y0, but we have to differentiate this one, sorry, y, with respect to y. So we have 1/2 and square root of y. Got it? And what about the second term? You have negative density of x evaluated at negative y. And you differentiate that one, negative becomes positive, and you have what? 1/2 square root of y. Okay? And then this goes away. So you have this interesting result, and this only holds for y positive. What if y equals 0? Then you differentiate that one, and you have 0. So you have for y equals 0, and for y less than 0, you have 0. Okay? So density function of y definitely is related to the normalized histogram of y, and y value is square of x squared, so you can never have something here, right? So density function says this is 0, but actually single point doesn't matter, so you may have something like this. Got it? Okay, so squaring device has something interesting. You have two parts of the PDF of x scaled by the square root operation, and also scaled by the inverse square root of y. Anyway, so by doing this, you can find theoretically any CDF of the output of random variable. But if the function is very complicated, for example, it's not scaling device, it's not monotone, then what can we do? There is a very interesting result by using Jacobian, and we will see it again in multiple random variable case, but here we are going to focus on single function of a random variable. And this is very interesting. By the way, from here, we assume that G is differentiable, okay? Of course, when we talked about monotonicity, we could assume that G prime exists. But from here, the existence of the derivative of G is very important. So let's see, what is the Jacobi's method? Jacobi's method is related to the idea of using this type of thing. So we generalize that. So let me draw something interesting. So here, suppose you have some non-monotonically varying function. So this is x, and this is g of x. And now the question is, given the PDF of random variable x, what can you say about the PDF of y? And the idea is also related to the scatter plot of y, histogram of y, its limit as the PDF of y. So what we do is that we just divide the y-axis into smaller bins. Okay, that is the idea of scatter plot, right? See that you have a box, and here goes G, and you have X, and you have output, and here you observe Y, and Y may have some value, for example, in this interval. Now, sorry, let's focus on this interval, okay? Suppose you have bins and you have histogram, and you focus on some bin that corresponds to this interval. Then when do we have realization in this interval? So what you do is very similar to Lebesgue's idea for integration. You draw two lines, right? And then you find the x intervals on which realization of x falls into this bin. So if you have some value x on this interval, then you have the yi value, or at least the value represented by y sub I. But interestingly, since g is not monotone function, you have more than one interval. Here again, and here again, and here again, right? So in this y sub I value, you have how many? Also here in this interval, right? 1, 2, 3, 4, 5 intervals for x corresponds to this interval in y. Now, how many realizations? So this probability, the probability of event that your x resides here, let's say that probability as p sub I1, and this probability, p sub x I1, p sub x I2, something like that, right? And your p sub y I is the sum of that ones. Now, if I say something like this, you may not be surprised any longer. So what I'm claiming is that the density function of y, which corresponds to some limit value of the height of your y histogram, right, is the summation of what? Of these things. So you have density function of x evaluated at, so you have some y, and as I told you, y1, y2 something. So your index is a function of y, right? So let me use index set as index of y, okay? What does that mean? If you choose some value y here, then how many zero crossings? 1, 2, 3, 4, 5. And this index set consists of 1 through 5 in this case. And you have x of y and I, okay? Because your total probability within this bin is kind of summation, actually weighted summation of the density of x evaluated at corresponding x values, right? And here goes something similar, something interesting. You say that here goes dy dx evaluated at x of yi. Okay. And here, what is important is this one. Here, y equals g of x. So dy dx is simply g prime of x. And g prime's argument must have axis unit. So you evaluate at this value. But here, you have something interesting, absolute value. Why do you have that? You may justify this one. This is a density, right? And this is related to the probability within infinitesimally small interval. That must be the sum of weighted probabilities. And this is non-negative. And if this G prime is negative without this absolute value operator, this entire thing could be negative, and that doesn't make sense, right? So as you have seen already in this affine case, see that? This is also the scaling of the probability density of input. You see, if A is negative, then you have negative A. So actually, in many textbooks, combines these two and write it this way. Density of Y equals f of x evaluated at y minus b divided by a divided by absolute value of a. And this absolute value of a kind of is what? Y dy dx, right? Because y equals ax plus b. So you have in the denominator dy dx absolute valued. Similarly, you have what? Here in Jacobi's method, you have dy dx with absolute value. Okay? So this is a way to memorize Jacobi's results. And we will see it again in random vector case. But you need a lot of exercises, so I'm going to leave the details to you. For more precise derivation, you can consult my old lecture, EECE574, undergraduate probability and random processes course. So you view that video and also use the course material. Okay. Okay. So I believe we've done here, and you can redo the squaring device case. So here, let's see. We derived this density of the squaring devices output using the CDF and then differentiating. We can directly use the Jacobi's method to find that. So first thing is that we draw the graph of G, which is y equals x squared. And we can easily see that for y non-negative, we have 2 points. So our density function, if y is greater than 0, is a summation of 2 density functions of x. And of course, given y0, you have square root of y0 and negative square root of y0, which is reflected as square root of y and negative square root of y. And we remember from here and also from here, in the numerator, we must have the absolute value of the derivative of that transformation function. What is that? Y equals x squared implies dy dx equals 2x. So this is 2 times square root of y, absolute value, and 2 times negative square root of y with absolute value. But this can be written as 2 times square root of y. And you can suddenly notice that, hey, they are the same, right? Got it? So this squaring device example also reinforces how to memorize Jacobi's results. In the numerator, you have the probability in terms of the density of x, the input, and in the denominator, you scale it by using the first order derivative of the transformation function, mapping rule G. Got it? So that's all for this transformation part. And you may say that, Is it really that so? No, we have one more section that is entitled as the computer generation of a random variable. And it's a very interesting topic because for our simulation of, for example, communication systems, we usually use random number generator. However, we cannot have purely random number generator unless this random number generator is governed by quantum mechanics. So what we do is that we do not use fully random number generator, but implement a pseudo, in Korean, 의사 또는 유사 random number generator by using, for example, nonlinear feedback loop or something similar. By the way, you may think about implementing purely random number generator based on quantum mechanics, and actually that is done by the British people long ago when they choose the lottery number. So it's like on Saturday night, we have a Korean lottery called Lotto, and we usually use some mechanical random number generator, including a lot of balls and something like that. But these British people, once they no longer exercise, but once built a quantum mechanics-based random number generator to choose the winning a lottery ticket. Quite interesting. I've seen that in the Science and Technology Museum at London, and you will find it if you visit. Anyway, so our human being has a technology to generate pseudo random number. But what kind of pseudo random number we must generate? There are uncountably infinite cases of random number generators. For example, if X is Gaussian, then what kind of random number generator we need? If U is uniform, what kind of random number generator we must have? Something like that. So there have been a lot of different distributions, discrete, continuous, mixed. And for each distribution, do we need new pseudo-random number generator? The answer is no. And interestingly, the theory says that as far as we have a uniform random number generator, then we are happy. So from a uniform 0, 1, we call uniform 0, 1 or standard uniform, continuous uniform random number generator, we can generate any random number, any distribution. That is the result we have to remember from this section. Then the question is how, right? So let's do this. What we want to do is that we have a uniform 0, 1 random number generator. And from the output of this uniform random number generator, can we, yeah, you are right. Can we find this G that makes the output, let's say X, as we desired? For example, can we find the G that makes X a standard Gaussian random variable, X a Rayleigh random variable? Not only that kind of continuous random variable, can you find mapping G that generates a discrete random variable, something like that? So let's see. The simplest case is what? X is also uniform. So let's consider some transformation where the output is also uniform 0, 1, and you may say that identity function. So your claim is this one. So here is U. I will just denote U as the standard 0, 1 uniform. And you may say that here goes the identity function, then you have U. So this function G is what? G of something is, in this case, x. That is the identity function, right? So x is mapped to x. But what if I say that, no. Let me see, x equals u. What if I say that x equals 1 minus u? Let me say y, okay? Now you know that in the upper branch, you have x equals g of u, which is u. So this is u, and this is x for u. And the lower branch, y equals 1 minus u. For all u, you have this mapping. U is mapped to 1 minus u, which is y, right? And my question is, y is uniform? Y is uniform 0, 1? And what is your answer? So in order to have an intuition to this kind of problem, as I always told you, consider a scatter plot and histogram, something like that. So what you do is that you consider the histogram of the input u. So you have 0, 1, and a lot of bins. And if you generate millions of u's independently, then you have something like this after proper normalization, right? And what happens to this bin? In the upper branch, it is mapped to this bin, but on the lower branch, it is mapped to that one. However, you already know that if we generate a lot of u's, this will look like a rectangular pulse. Then you will also have rectangular pulse for the x and y. What does that mean? Yes, y is also uniform 0, 1. So the first result you have to remember is that such a transformation that generates the desired output distribution is in general not unique, as you've seen here. Input is u, and your output is uniform. One way is to have an identity map. The other is 1 minus identity map. Got it? So quite interesting. So given non-uniqueness, what would be our task? We find something very easy to remember. And this is related to the inverse CDF, which is the inverse function of the CDF. And the other is the so-called percentile function. And percentile function is sometimes the same as inverse CDF, but they are not exactly the same. And I will talk about that more in detail. And it seems I need more space. So let me enlarge this part. I hope I can finish this supplementary lecture today. It seems I'm talking too much and explaining too much details, but it's really important. Okay, so let me proceed. So let's focus on the first case where we have uniform 0, 1 input and some mapping rule with a discrete random variable x. So we already have the CDF of this discrete random variable, or PDF of this discrete random variable, or PMF of this discrete random variable. Actually, from this, you can find that. From this, you can find that. Of course, they are interchangeable. And what I do is like this. Let's just consider a very special case, like x takes two values, x1 and x2, with probability 1 and probability 2. Of course, P1 and P2 are positive values for simplicity and less than 1, and they sum up to 1. Now, this is the PMF. What kind of mapping do you want to use to have X following this probability mass function, P1 and P2? And it's not that difficult because anyway, you want to find something like this and also consider that scatter plot and histogram. So U is kind of consisting of, if you generate a lot of independently generated outcomes of U, then you have a lot of dots here, uniformly scattered. And what you do is that you just divide the interval into 2, and this length is P1, and this length is P2. Then what you do is that this value is X1, and that value is X2. So something like this. Then what happens? Whenever you have U value from 0 to P1, it is mapped to X1, right? So the value X1 will have probability P1. And if you map the U value from P1 up to 1, whose difference is P2, then you have X value X2. So at X2, you have probability P2. So this is the way to construct G of X. Okay? This is one of G of X. I'm not saying that this is the unique way. Why? Because you can have a lot of variations. For example, you can first choose P2 and maybe to X2, and then this area for X1. No problem, right? Still, your output will have value X1 with probability P1 and value X2 with probability P2. Or you can divide and put this in the middle, and you divide this interval into many, many cases. But this looks something similar, right? What is this one? Yeah, this looks similar to your CDF inversed. And if I say that, what? So let's take a look at the CDF of this discrete random variable. What is that? So CDF of X has jump discontinuities at X1 and X2. See that? Up to X1, your CDF value is 0. And suddenly, it jumps to P1, right? And stays there, and it jumps to, not P2, 1. This difference is P2, right? So this is the CDF of X, right? And what if you flip the x-axis and vertical and horizontal axis? Let's say this is Y. Okay. Y value is always bounded by 0 and 1 because Y value is probability. And now, what else do we have? So here, at X1 and X2, you have this line stays up to here, and that line stays here, right? And that line, sorry about that. This is P1, and this is 1, and you have that, okay? By the way, this conversion from the left-hand side to right-hand side is just what? It's just you rotated the axis after, of course, flipping X and Y. But this is not a function, not a function. So what people devised is that they made it a function, which means that for these values, you connect this vacant interval and also connect these two. Then what do you have? You have a new function defined on this interval, y between 0 and 1, and which is x1 for this value and x2 for this value. What is this one? Exactly that one. Okay. So this is the hint. You use the kind of inverse of the CDF. But sometimes if you have the jump discontinuities in the CDF, you can't use that. In that case, you find a function. This function is called, this derived from the inverse, possibly, or derived from the CDF, is called the percentile function. So this is the percentile function. The reason why this is called the percentile function is that if we view the vertical axis as the percentage, then if you, the horizontal is percentage, then you can find the value. So this is 0%, this is 100%. So your argument is percent, and you can find the score. Okay? So if you want to find 99 percentile, then what is the score? X2. If you have, for example, 10 percentile value, it's X1, something like that. So the percentile function is very useful in finding the mapping rule that maps a uniform distribution to a discrete distribution. What about continuous case? And here goes the continuous case, which probably your undergraduate professors proved a lot. So I'm not going to prove that, but give you a different point of view. So now consider X a continuous random variable. By the way, what was the definition of continuity of a random variable? Continuous random variable. Its CDF is continuous, right? However, fx is a continuous function does not imply its inverse exists. Why? Because sometimes, even though the CDF is continuous, it may have a constant interval, right? In that case, if you flip the left and right side, then what do you have? Some non-function because of this period, right? You cannot have multiple values assigned. One good thing is that you define, so you define or call f, capital F sub x, inverse of x as the percentile function. Then what happens? You redefine this one so that you have something like that one, okay? You may either, usually you include the upper side because you want to write continuity here, something like that, but it doesn't matter anyway. So you have something like this. Got it? So now let me see. Let me use the whether this inverse function, okay, sorry, this must be u, this is x, right? And you have uniform, and let's calculate the CDF of this. Let's say this has temporarily y, then what is the density of y? Probability of event that capital Y less than or equal to y. What is that? F sub CDF of x inverse, actually percentile function, evaluated at u is less than or equal to y. And good thing is that you can easily find the equivalent event because percentile function is always monotonically increasing. So you have some value like this, okay? And let me see, just a second. Yeah, am I correct? Yeah, I believe so. So this is CDF of U, right? Evaluated at f of y. Now, by the way, this value is between 0 and 1, right? And let me ask you, what is the CDF of U? CDF of U is very simple. It's flat or negative. It's an identity for input 0, 1, and it flattens to 1. So as far as this argument is between 0 and 1, this output is CDF of y, right? So what? The output follows the CDF of x. So we can say that this is a y, this is an x. This is a random variable that follows the CDF or that follows the distribution of x. So this is our answer. Be careful. This percentile function, okay, this is a kind of inverse of the CDF, is not the unique choice because you can always flip it. For example, you can replace it with percentile function of 1 minus u because 1 minus u is also uniform. So if you flip it, no problem. So anyway, the mapping rule is not unique, but using the percentile function is a good choice to generate an arbitrary, discrete, continuous, mixed random variable from a standard uniform 0, 1 random variable. Okay, so I believe that's all for the day. Oh, by the way, not that's all for the day. I skipped last one. So another one. Okay, let me start. Let me not stop here. So another thing. So here we have something interesting. So if you have uniform and you have the percentile function of x, then you have x. What about you put here the CDF of x? Then what would be this question mark? And from just our middle school math, if we have some function f and composition of its inverse becomes what? Becomes identity, right? So here you have some uniform random variable. What does that mean? Now take a look at that part only. What does that mean? If you transform a random variable using your CDF, then you can get a uniform random variable, right? But you shouldn't stop here because if x is discrete, this doesn't work, right? So this only works continuous x, especially if I remember continuous random variable x, not even mixed random variable with point mass. So be careful about that. That's the last message of today's supplementary lecture. That's all for the day.